This topic has a reputation, and the reputation is it is boring and mechanical. Okay, maybe not topic. This concept, this process. Okay, now that reputation is justly deserved in some ways. Sorry, that's okay. Because, as you'll see, we're going to learn two methods for doing this, and both of them are quite mechanical and repetitive, okay? So what I'm going to try and do is introduce these two methods by drawing you back to, like, when did you first learn this? I think it must have been about a year ago when we were doing integration, a bit less than a year, and we looked at not approximating roots or solutions, but approximating areas. Now, we've got two colors here. You remember that when we learned integration, okay, one of the cool things was that it seems kind of weird that when you differentiate, which is calculus in one direction, you get gradient, and when you integrate, you go the other way, you get area. And like gradient, area, like they don't seem like they're opposite to each other. But we established it mathematically, we showed that it was the case, right? So if you want the area under the curve, you can say that at least this area in particular is given by a definite integral. Okay, so we connected calculations of a geometric property, okay, with this strange process. So this integral here, that would give us the area that we're after. Yes? But as you're familiar with, not every function can be integrated. In fact, if you think about it like in the grand scheme of things, most functions can't be integrated with nice, neat analytical methods. You just raise the power and do this and divide and so on. We sort of focus on the kinds of functions that you can integrate. So it sort of feels like, oh yeah, I can integrate like 90% of the stuff that's out there. But if we learnt more kinds of functions, you'd be like, oh, can't integrate that, or that, or that. Oh, there's one I can do. And then the rest of them, you just can't touch them, okay? But you can still work out the area under the curve for functions like that. You just can't get precision, okay? So we learned two methods. Do you remember what they were? Two methods for getting approximate areas under curves. There was the simplest one, which was just taking a polygon, and it was a trapezium, right? So we called it trapezoidal rule. So it was taking that and then drawing however many subsections, and we know how to find out the area of trapeziums. So that's fine. Okay. We also learned another method, a more clever one. What was it called? Simpson's rule. Now that's its name, but how did it work? It wasn't using a trapezium or any other kind of polygon. What were we using to approximate the curve? A parabola, right? Which is actually, when you think about it, it's really smart. You pick 3 points, and this is not a parabola, okay? But if I pick 3 points on here, 1, 2, 3, you could draw a parabola that's pretty close to it, right? That would pass through all those points, something like, I don't know, maybe something like this. Okay, so that could be a parabola, and you'd get really, really close, right? Much closer than a trapezium, okay? So these methods are actually quite, they're quite thoughtful, right? They're taking a problem, which is difficult, integration, okay? And they're not getting the exact answer, but they're getting pretty close with some pretty smart tricks, right? Okay, so there's these two, right? Now what's parallel to this is when you think about if you're trying to solve an equation, right, find its roots, okay? So let's draw a graph, and this time, you don't have to draw that, but draw this with me, okay? If you have, say, quadratic, right? For quadratic functions, we know how to find their roots and their solutions, right? Even if they're really weird, gross, imaginary, complex, we have a formula for it, right? But once you step it up a little bit, okay, if you have any polynomial of higher degree, right, you're kind of stuck, right? The cubic formula, which exists, is terrible, right? It's really, really long. It's very awkward to use. Doesn't even work in all the cases. Doesn't work for all kinds of cubic functions. And if you raise the power, it just gets worse and worse and worse, okay? So how do you find, if there was a root there, how would you do it, okay? Now, much the same way as you can find the exact root if you know how to integrate, and you can find an exact root if you've got a particular kind of function, like a quadratic. We can't find the exact root, but we can get pretty close, okay? And just like with before, there are two methods, okay? So I'm going to teach them to you. We'll do them one at a time. So today, we're going to look at what's called the bisection method. It's often also called halving the interval. I'll explain why in a second. Well, maybe you can tell me why after I show you how it works. which sort of like trapezoidal it's a very blunt tool. It's not very smart, but it works. But because it's not very smart, it's a very slow method, as you'll see shortly. The second method is smarter, but it's more sophisticated. It uses calculus, and it's a little more notorious. It's called Newton's method. So Simpson's rule, Newton's method. I don't know what it is with people naming, rules after themselves, but that's what they are. So let's cover the bisection method today, right? Now on this graph that you've drawn, I want you to imagine, let's suppose for this particular graph, okay? We know that there's a root somewhere, okay? And the thing about these continuous functions, that's important by the way, both of these methods, they only work for continuous functions. You have a think as I explain them, these two methods, you have to think about why it wouldn't work if there was a discontinuity, okay? The thing about continuous functions is that if you know some value for the graph, like say here, okay? Let's suppose that that's, I don't know, let's call that 1, okay? When you test out this value, if this is f of x, okay? If you put in 1 and you substitute it in, okay? You would see that f of 1 is negative. Okay, so it's below the axis. That's geometrically what it means. Okay, and if you go further along, let's just say another value like 2. Okay, so if that's 1, 2, so something like this. If you evaluate f of 2, it's positive, right? Okay. Now, if you're a continuous function, right, you can't change sign, go from negative to positive, or vice versa. Okay. You can't change sign without passing through the axis at some point. Okay, see that's why it's important that it's continuous, right? Because if it was discontinuous, it could be negative here and then disappear, have an asymptote or something like that, and then reappear on the other side. Okay, but if it's continuous all the way through, if you go from negative to positive or positive to negative, you've got to have a root or a solution in there somewhere. Okay, so let's take this example. I need my whiteboard eraser. And let's go with it. Here, I'm going to say, right, f1. I don't need to know what this function is for now, okay, just so that I can explain what the method is, okay? f1 is less than 0, okay? But f2 is more than 0, okay? Therefore, there exists some f of... Now, we want to actually have some specific value. Okay, so I'm just going to call it x0. Okay. There is some place where that's equal to 0, right? But not just that. I know it has to be between 1 and 2. It's got to be somewhere between these. Okay, such that x0 is between these two values. Okay. So if I know it's between there, right, what I can do is I can do a little more testing. I tested two values here to get a little more precision, to kind of narrow down where it is. Okay, so this is called the bisection method, right? So I'm going to try and get some more precision by taking this interval, right, and halving it. So I'm going to test another value. Now, just on my diagram, just roughly speaking, okay, if I put 1.5 in there, okay, I can see in this case that f of 1.5 is up here. Okay, so I test f of 1.5 and I find it's positive. Okay, so what does this mean? Well, if f1 is negative and f2 is positive, from here, 1.5 to 2, it's still positive. So the solution is not in there, right? It's going to be somewhere in this little interval, right? So I can continue going. I can go from 1 to 1.5. Halfway is 1.25, right? So I'm going to test again. Now, at least on my diagram, 1.25 looks like it's the actual root. Okay, so my diagram is going to not be very helpful here. But just suppose, okay, suppose that it was just beneath the axis. Okay. Now, what does that tell you? That means that the root must be between 1.25 and 1.5. See how there's a change of sign, right? So there's my 1.25 just to the left, okay? So I don't know what the exact value is. I'll get some decimal out when I evaluate the function 1.25. but I'm going to get closer and closer and closer, right? So for instance, at this point, I can say, if I wanted to say to 1 decimal point, okay, I can say it's either 1.3 or 1.4, right? So if I halve the interval again, if I bisect again, I know I'm going to be closer to one or the other, and then I can say, after 3 repetitions of this method, I can say, oh, it's going to be approximately 1.3 or approximately 1.4, whichever it turns out. Okay? So does that make sense? Can you see the mechanic behind how it works? You can also see why people find it quite boring and mechanical, okay? But it's quite clever when you think about it in terms of like, how else would I solve this problem? Okay? Bisection method, it's very mechanical and it's very simple, okay? But despite the fact that you can do it quite mindlessly when you're going through all the steps, okay? You can't just pick things blindly and just go for it. What I mean is, these 2 values you start out with, like these 2, okay? You have to be careful when you choose them, okay? And the obvious example is where you've got multiple roots that are close together, okay? So suppose, I don't know, my scale's a bit off, but suppose that was 1 and that was 2, okay? Just, yeah, bad scale, but you get the idea, okay? Obviously here, you'll see when you test F1, you'll get a negative, and when you test F2, you'll get a positive, okay? But all the bisection method will do is establish that there must be one solution between those change of signs, okay? So the first thing is you're going to omit solutions, like, you know, you might eventually only wind up at one of them, okay? But depending on how they go, but anyway, you'll miss some solutions, okay? You'll miss a pair. But secondly, when you actually start to test out values, they'll go all over the place because there are more changes of sign in there than just the simple one that you can tell, now I'm on the left, now I'm on the right, and so on. Okay? So make sure you actually pick out, if they don't tell you, right, where, they don't give you a vicinity, you have to be very careful when you actually pick your values to make sure that you only got one solution in there. And you'll see the same kind of problem, picking your value carefully, that applies to Newton's method as well. Okay? So just make sure you have a note of that you have this kind of diagram, and you make sure to avoid having multiple roots between your 2 testing points. Okay? And that's basically all there is to bisection method. Okay? I reckon probably you can pack up. I think the bell's going to go soon.